Alright everybody, today we're going to talk about a particular way to visualize compounds called Newman projections. I don't know if any of you have any familiarity with the TV show Seinfeld, but hello Newman is a reference to that TV show. Anyway, Newman projections. Now when you look at a alkane, you're used to seeing something kind of like this. So we've got a 4-carbon chain with a methyl group sticking off it, 2-methyl butane. Alright. Now the one thing that you can't really see here are all the different conformations of that molecule that you can have. Alright. So if I was to draw that molecule out, or rather on this molecule put on all the pieces that aren't currently showing, so here is a CH3, here is a CH3, there's another CH3 or methyl here, and then the other two places on this carbon, that's a CH2, and then coming off this carbon there's a hydrogen. Alright, so can you see here we've added in all of the groups that weren't in that structure before. Alright, now imagine that I count, or that I number these carbons. So I'm just going to say this is carbon 1, carbon 2, carbon 3 and carbon 4. Now in Newman projections you're actually looking down a carbon-carbon bond. So imagine that this is your eye. This is my fabulous rendition of an eye. Believe me, that's not something else. That's supposed to be an eye, an eyeball. And you are looking down the carbon 2, carbon 3 bond. Alright? When you're doing Newman projections you always need to specify which bond you are looking down. In this case it's carbon 2 and carbon 3. Now in Newman projections there's a very particular way to represent carbon 2, which is the front carbon, and carbon 3, which is the back carbon. And before we start drawing those, can you see that when we look at carbon 2, coming off that carbon is a methyl, and a hydrogen. Whereas coming off carbon 3 is a hydrogen, and a methyl. Now this is an alkane, so you can freely rotate around all of these bonds here. We are going to imagine just rotating around the central carbon 2, carbon 3 bond. So on the next slide here I'm going to show you what Newman projections look like, and I want you to keep this 2-methyl butane, this structure in mind. Alright. In fact, let me draw that structure out here just so we have something to look at as a comparison. Okay. So with a Newman projection there's a very particular way that you show things, and that is that the front carbon is shown by a dot, and that would help if I actually put it in the middle there. The front carbon is shown by a dot, and I'm going to try and put it right in the middle of the circle here, and I'm going to try and do that for all of these. Dot, dot, dot. So these circles with dots in them are going to represent different conformations of this 2-methyl butane. And so remember we said we were looking at carbon 2 and carbon 3 down this bond. In a Newman projection the front carbon, in this case carbon 2, is represented by a dot. Carbon 3 is represented by this large circle here. So carbon 2 is the front, carbon 3 is the back. Now remember we said that coming off carbon 2 we have a methyl, and a hydrogen. And the way we usually show this in a Newman projection is we draw out 3 sets of bonds looking like this. Alright? And then on carbon 3 we said there are also 3 groups coming off here, a hydrogen, and a methyl. So we have to show a way that the carbons are coming off the back carbon, and we do that by showing bonds like this. So front carbon, back carbon. Alright? So we're going to go back to our front carbon. There's 2 CH3s and a hydrogen. At this point it's totally up to you as to where you want to put those groups. So I'm going to say there's a CH3 here, there's a CH3 here, and there's a hydrogen here. Alright, that's the front carbon. We'll just label that as carbon 2. The big circle here is carbon 3, and remember we'd said on carbon 3 there's a methyl, a hydrogen, and a hydrogen. So I can put the methyl wherever I want to. I'm going to put the methyl here, and then the 2 hydrogens here and here. So can you see that I have now drawn out one conformation of this Newman projection for this 2-methylbutane? All right? And the whole point behind doing all this is to see which of all the conformations I'm going to draw is the most stable. All right? And to do that, we have to take into account the fact that we can freely rotate around all these bonds, and we're focusing on the carbon 2,3 bond. And between each of these conformations, what we're doing is saying we are rotating 60 degrees. Because if you imagine this is a circle, I can rotate 360 degrees by doing 60 degrees 6 times. All right? You can rotate to the left or the right, or clockwise or counterclockwise, however you want to do it. So the way I like to do things is rotate clockwise. Sorry, I don't know what's going on with this bloody thing. And the other thing about Newman projections is you want to make sure that you keep either the front carbon or the back carbon constant. So you either move the stuff on the back carbon or the stuff on the front carbon. I like to keep the stuff on the front carbon the same and just move the back. So what that means is I'm going to draw out the stuff on my front carbon exactly the same as it was before. Those funky looking H's are just my software screwing with me. And dude, what the hell is it doing now? Bloody thing. Alright. So if I move the back carbon 60 degrees, can you see that this makes this CH3 come right where this one is? So here these two CH3s are going to be right on top of each other. Now of course I can't show them right on top of each other because then I couldn't see what's at the back. So what I do is I just show the CH3 here. It isn't exactly behind it, but I just draw it as accurate as I can as being behind it. So if I move everything on the back carbon 60 degrees, can you see the CH3 moves down, the H moves here, and then this H moves here. Okay? Now, there's a particular name for these different conformations. The name for these guys, when I have all the groups displaced like this, is called a staggered conformation. Eclipsed is when everything is behind everything else. All right? So let's see what would happen if I rotate again 60 degrees. All right? Remember that I'm keeping what's at the front exactly the same. Sorry, that CH3 bond was supposed to be straight up. That's just my crappy drawing skills. So notice that I'm keeping the front carbon exactly the same, and I'm just going to move the back carbon. So first I had staggered and I rotated 60 degrees to get to eclipsed. If I rotate from eclipsed 60 degrees, this hydrogen goes here. So I go back to staggered again. So I'm going to have staggered here and here and here. So what group do you think is going to be down here? Well, if the back carbon's moving, it's going to be my CH3, so I'm going to put that there. And then when I move up here, the hydrogen moves up and I get to staggered again. So can you see we're doing staggered, eclipsed, staggered. So what do you think this one's going to be? Well, no prizes for guessing. It's going to be eclipsed. Again, we're going to keep the stuff on the front carbon exactly the same as it was before. Alright, so CH3, and then we've got the hydrogen here. I'm going to draw on my eclipsed bonds in just a minute. So the question for everybody is now, well, what bond is going to be eclipsed with my CH3 up here? And it's going to be this hydrogen. So I'm going to draw that there. What group is going to be eclipsed with this CH3 here? And it's going to be this hydrogen. So I'll draw it there. And then the group eclipsed with this hydrogen, of course, is going to be this methyl. All right. So like I said before, you can see that I haven't drawn the eclipsed groups right behind each other, but I've drawn them in such a way that it's clear to tell the difference between staggered and eclipsed. All right. So what's the next one that I'm going to? Well, of course, it's going to be staggered. Once again, I keep my front carbon groups exactly the same. All right. So I'm drawing everything on my front carbon is exactly the same as it's been all the way through. All right, I'm going to put my staggered bonds here because I know I just had an eclipsed. So what group is going to go here? Well, remember, each time I'm rotating 60 degrees to the right, or clockwise, however you want to look at it. So it's going to be a hydrogen here a hydrogen here, and a CH3 here. Alright, now the last one here, CH3, again, I don't know why this keeps on doing that with my bloody hydrogens. Damn thing. Anyway, everything on the front carbon stays exactly the same as it was all the way through. And of course I'm going to have an eclipsed here. So now can you guys see that I'm going to have two CH3 groups eclipsed? I'm just drawing the CH3 that way because I don't really have enough space to draw it the other way. I got two hydrogens eclipsed here, and then what have I got here? Well, I've got a hydrogen eclipsing with a CH3. Alright, and can you guys see that if I rotate it again here, I get back up to this guy. Alright, so can you see I have 6 conformations at this point? So this is part of the theory of Newman projections, and once we've done this, the thing we have to look at now is we have to look at relative stability. In other words, which of my conformations are more stable? Now I imagine that you can probably guess. If I ask you, is staggered or eclipsed more stable? Well, in general sense, you'd probably say staggered is more eclipsed, because staggered is more stable, I'm sorry. Because in the eclipsed ones, everything's much closer together. But can we actually quantify that? Can we actually come up with energy values for each of these different conformations? Well, it turns out we can. Your textbook has a list of energy values for each destabilizing conformation, and I have these written here. If I have two hydrogens that are eclipsing each other, that increases the energy of my molecule by this amount of energy. Eclipsing CH3 and H, because the CH3 is bigger, is a larger amount of energy. Two CH3s eclipsing is even bigger because they're bigger and closer together. Now gauche CH3 groups, this is the one energy value for CH3 groups that are staggered. Alright, you can see the rest of the energy, the rest of the interactions are all eclipsed. Gauche is for when we have two CH3 groups that are staggered but right next to each other. Alright, so for example, can you see on, for example, this conformation here, this CH3 is kind of by itself, but these two are right next to each other, so these are gauche. These two are next to each other, so these are gauche. And in this one, these two are next to each other, and these two. So here there's two gauches, here there's one, and here there's one. So let's go through each of the conformations and see if we can figure out the total energy of each. Alright? So these are the numbers, and I'm just going to keep referring back to this table as I need to. So let's look at the first conformation. Can you guys see I have one gauche interaction and one gauche interaction. All the hydrogens are staggered to each other, and they're too small to have any interaction. They're also too small to interact with the metals, but the metals are big enough to interact with each other even though they're staggered. So that means I have two gauche interactions. Each of the gauche interactions has an energy value of 3.8 kilojoules per mole. Therefore, this conformation has a total energy, can you see, of 7.6 kilojoules per mole. Alright, does that make sense? We're going to do that for each of these. When we get to this eclipse conformation, you'll see that the energy is a lot higher. Alright, so can you see we have one hydrogen-hydrogen eclipsing conformation. We have one CH3 hydrogen eclipsing conformation, and we have one CH3 eclipsing conformation. Alright, each of these has a particular energy. Alright, the hydrogen's got an energy of 4 kilojoules per mole, the CH3H is 6, and the eclipsing is 11. Meaning this is 4 plus 6 plus 11, meaning there's obviously much higher energy in this conformation than this one. 11 plus 6 plus 4 is 21 kilojoules per mole for this conformation. Obviously much higher than this one. Now let's go on to this next one. Can you see here the only interaction is this gauche interaction? That's all we have. So therefore that has an energy value of 3.8 kilojoules per mole. When we go on to the other staggered one, we're going to come back to this eclipsed one. Can you see it's exactly the same here? So this also has an energy of 3.8 kilojoules per mole. Now let's go to the remaining two eclipse conformations and let's see what we've got. Can you see we've got 3 times what have we got here? What do we have here? We have 3 times CH3 eclipsing conformations. Alright? Now each of those has an energy value of 6 kilojoules per mole, therefore 6 times 3, giving a total energy for this conformation of 18, sorry, I don't know what's going on with my pen here. I think it doesn't like me or something. 18 kilojoules per mole. And let's have a look at this one. Can you see here we've got a hydrogen-hydrogen eclipsing conformation, a H and a CH3 eclipsing conformation, and then a CH3-CH3 eclipsing conformation, just like we have here. Therefore, this one also has an energy value of 21 kilojoules per mole. So then the last question here is, which of these conformations is the most and least stable? Well, of course, the one that's most stable is the conformation or conformations that have the lowest energy, and that is this one and this one. As you would imagine, these are staggered. The conformation or conformations that are least stable are the ones that have the highest energy, which is this one and this one. And that, in a nutshell, is how Newman projections work. There's nothing more to it than this, and hopefully after watching this video, when we do these in class, it'll make more sense. Alright? Thank you.